So we're talking about graphs, and graphs are a very important topic in computer science. We're just talking about the basics here in this course. If you take a course like analysis of algorithms, you'll see a lot more about graphs. So we start with well, a few types of graphs, but the one we're going to start with is called a simple graph. So we have a simple graph. We'll give it a name like G, and it has two parts. So we say that G, this simple graph, is a pair of two things, V and E. And V is a set of objects, which we call vertices. The singular of vertices is vertex. So these things here, these, you can call them nodes or vertices, like A and C and B and H and so on. These are the vertices. So a graph contains a set of vertices, V, and a graph also contains E, which is a set of edges. And the edges here are represented by lines. Each edge, but technically each edge is a set of exactly two vertices and indicates that the two vertices are connected. So we draw it as a line here, but really, more technically, it's a set of two vertices, namely C and B, and it indicates that C and B are connected. So here's a simple graph. We have these vertices, right? So the set V is this set, A through I, right? A, B, C, D, E, F, G, H, I. So this whole thing is one graph, even though they're not all connected to each other, right? You have some things that are not connected to anything, some things that are separate from the main part of the graph, but this is one big graph. And the set of vertices is this. And then the set of edges. So we have an edge from between A and C. So we put A comma C as a set like this. So again, E is a set starting here and ending here. And inside that set, there are little sets like A comma C, A comma D, and so on. Now we have this A comma C. Should we also have C comma A? Well, the thing is, we shouldn't, because this set A comma C is the same as this set C comma A. So it would be redundant to have it twice. And the point is that in a set, the order doesn't matter. So A comma C and C comma A, the order doesn't matter. And the point is, what this set represents is a connection between A and C. So, but the connection is not directional. It's not like you can go from A to C, but not the other way around, or you can go from C to A, but not the other way around. It's just, it's like a two-way street. So this is at least how it works in a simple graph. We'll see a different type of graph later on where there are arrows, but for now, we're not dealing with that. Now, you might wonder, can we have a edge going from a vertex to itself? For example, can we have an edge going from B to itself? So here it is. A simple graph cannot have an edge, let's say V comma V, the set V comma V from a vertex V to itself. And the reason, well, one reason is because this is not a valid set. Remember, a set cannot have duplicates. So if we would try to have an edge, let's say from B to itself, the edge would be the set B comma B, but that's not a valid set. So therefore, we cannot have edges from a node to itself, from a vertex to itself. All right, now another definition. If we have an edge, remember an edge is a set of two vertices, and it indicates that the two vertices are connected to each other. So if we have this edge, U comma V, then we say that U and V are adjacent, right? So D and F, these two vertices, are adjacent because there is an edge connecting them. D and C are not adjacent, okay? Because there is no edge connecting D and C, even though there is a path between D and C, but that's not enough. For adjacent, we need them to actually be connected with a single edge. Okay, so, or A and F are also not adjacent. Okay, A and F, not adjacent. And then a similar definition is if we have an edge, again, U comma V, again, we're just here, U and V are just generic names for vertices. right? They're just like, they're very like X and Y, you know, they're just generic names. So if we have an edge E, which connects U and V, then we say that E is incident to U and V. So for example, this edge here, yes, this edge right here is incident to A and D. Okay, so an edge is incident to two vertices. It's incident to the two vertices that it connects to each other. Okay, now related definition, the degree of a vertex V, right? So if we have a vertex V and we want to know the degree of the vertex, what is it? So first of all, it's denoted like this, degree of V. So it is the number of edges that are incident to V. In other words, how many edges are coming out of it? All right, that's like, what would be the degree of C? Well, there are two edges coming out of it. There are two edges that are incident to C. So therefore, the degree of C is 2. The degree of D is, well, the degree of D is, it has 3 edges coming out of it, so it's 3, and so on. The degree of I is 1, because there's only 1 edge coming out of it. The degree of G is 0. Okay, so this is all straightforward, right? So just degree of A, let me move this up there. Just so we can make sure. So degree of A is 2, okay? Degree of B is also 2. Hold on. Okay, the degree of E is also 2. Then the degree of D is 3. Degree of F is 3. Degree of I is 1. Degree of H is 1, and degree of G is 0. All right. All right, so before we go to the next thing, let's just recall something that we saw, some kind of notation that we saw before. So if we have this, the sum over all x in the set 1, 5, and 10, x squared. So it's the sum of all x squared, where x ranges over the set of 1, 5, and 10. So that means x is first, it's 1, then it's 5, then it's 10, and you add all together. So you have 1 squared, right? So x squared, 1 squared, and then 5 squared, and then 10 squared, and you add them all together, you get 126. Okay, so we've seen that notation before. So we're going to use this notation very shortly. So let's actually try something here. What's the total degree of, what's the sum of all the degrees of all the vertices in this graph? Again, we have a bunch of vertices in this graph. Each vertex has a degree. If we take all those degrees and add them up, what do we get? Well, it comes out to 16. And, you know, you might notice that there are actually 8 edges. 1, 2, 3, 4, 5, 6, 7, 8. There are 8 edges, and the sum of all the degrees is 16. Okay, is that a coincidence? Well, no, because, well, here's the theorem. So suppose G, which has V and E, is a simple graph, then the sum of the degrees of all the vertices in G is twice the number of edges in G. In other words, the sum of the degrees of V, where V ranges over all the elements of big V, right? So little v, we're talking about degrees of each little v, where V is an element of big V, right? Big V is the set of all vertices. Little v is one vertex. So the degrees, the sum of the degrees of all the vertices is equal to 2 times the number of edges. And what's the reasoning? Well, each edge contributes to the degree of exactly 2 vertices, right? So each edge, every edge in a graph contributes to exactly 2 vertices. It adds 1 to the degree. For example, let's just take this edge here, right? This edge, it adds 1 to the degree of D, and it adds 1 to the degree of f. So every edge adds 1 to the degree of one side and 1 to the degree of the other side. So the point is that each edge contributes to the degree of exactly 2 vertices. That is, each edge adds 2 to the sum on the left, right? So this sum here, it adds 2 to it each time we have another edge. So the point is the total sum should be 2 times the number of edges. So this is a theorem that applies to all graphs. By the way, a theorem is just a proposition, but propositions that are considered important are called theorems, but it's just a proposition statement that is either true or false, and in this case, we prove that it's true. Another point I wanted to make, unrelated to that, is that the way you draw a graph doesn't matter, right? So if I would have drawn this graph by let's say taking h and I and moving them around. So let me show you. Right, so maybe if I would have drawn h over here and I over here and connected them like this and gotten rid of this, it would still be the same graph, right? Because the point of a graph is not the way it's laid out on paper. The only point of the graph is, well, 2 things. Which vertices do I have, right? So in this case, I have the same vertices, A through I. And what edges do I have? Meaning what connections, which vertices are connected to which vertices, right? So the exact way you arrange it on paper doesn't matter. It's still the same graph.